So I've got a signal XAFT that's band limited to 1.5 kilohertz. And I want to explore what happens if I take this signal XAFT and I sample it to get X of n for, let's try a couple different values. A, T is 1/4000th of a second, or 4,000 samples per second, or 4 kilohertz. If I sample at 4 kilohertz, if I sample at 6 kilohertz, and if I sample at 13 kilohertz. Let's explore what happens. This little notation of a wire that has an open connection and an arrow going through it is shorthand notation. That's the same thing for an ideal C to D converter. Usually you have to put a capital T up there to say how often it happens. Just like here I have to put a capital T. Okay, so for the first case, when T is 4 kilohertz, when T is 4 kilohertz, then my signal was band limited to B equals 3000 pi. So my discrete time signal is going to be band limited now to, in the case A, B times T is going to be 3000 pi times T, which is 1/4000. So my signal will map to 3/4 pi. Now, since B times T is less than pi, I know I don't have detrimental aliasing, so all I have to do is take the original signal, which was this nice ideal low-pass filter, redraw it to have height 1/T, so in this case it'll be 4000. In the range minus pi to pi, I just redraw the same spectrum. What used to be at 3000 pi is now at 3000 pi times T. So now this goes all the way out to 3 pi over 4 and minus 3 pi over 4. And it repeats with period 2 pi. Nice and simple. So as long as there's no detrimental aliasing, it's very easy to map the analog spectrum to the discrete time spectrum. You just take this picture, you copy it in the range minus pi to pi, and you scale it by capital T. So what was it? 3000 pi is now at 3/4 pi. That was case A. Now let's look at case B. Case B, we have T is 1/6000. So in this case, B times T is 3000 pi over 6000, which is pi over 2. So now the spectrum will look similar to before, but actually instead of going from minus 3/4 to 3/4, now we'll just go from minus 1/2 to 1/2. So minus pi over 2 to pi over 2. And the height is no longer 4000, it's now actually 6000. And again, this is pi, there's 2 pi. We have another copy sitting at 2 pi. My drawing wasn't so good, but looks the same, and it's periodic. This period, this is minus pi, here's minus 2 pi, height 6000, and so forth. And in case C, B times T is 3000 over, my notes said this is 12,000. Make it a nice round number instead of 13,000. 13,000 will make it ugly, so I'll make that 12,000. 3,000 over 12,000, or 3/12, which is 1/4, so that brings me to pi over 4. So instead of pi over 2, I now get half that width, 0, pi over 4, minus pi over 4. And the height is now 12,000 in at 2 pi and at minus 2 pi. So as I increase the sampling rate from 4,000 samples a second to 6,000 samples a second to 12,000 samples a second, the resulting discrete time spectrum goes from being band limited at 3 pi over 4 to being band limited to pi over 2 to being band limited to pi over 4. And the height scales from 4,000 to 6,000 to 12,000. So let's look a little deeper at the mathematical modeling of this A to D converter. Maybe it's not deeper, maybe it's shallower. I'll let you be the judge. So one of the ways that I like to think about an ideal discrete to or continuous to discrete converter is I like to think about what's going on inside this box as a two-step process. So I'll just draw a much bigger version of that box. Inside that box, there's really two things that are going on conceptually. This isn't how you'd actually build an A to D converter, but mathematically this is how you would build one. You take the analog signal XA of t, and the first thing that we do is we multiply that signal in the time domain by a periodic impulse train. I multiply it by an impulse train that's spaced capital T seconds apart. And then after I do that, I get a waveform, which was the original waveform, XA of t, whatever it was, multiplied by this impulse train. When you multiply those together, you get an impulse train where the impulses have different areas. I'll call this signal x sub s of t. So it's an impulse train where the areas of those impulses are equal to the samples of x of t at those times, 0, t, 2t, 3t, and so forth. Then we go through this operation of converting impulses to discrete time samples. And what comes out is x of n. So I derive the relationship